Assalamualaikum and good morning, wherever you are. Make sure that you guys stay safe. We are still have yet to overcome the COVID pandemic. Make sure that you guys stay safe. Although the government has decided to open up the economy, it doesn't mean that the COVID has been fully resolved. We have to stay cautious. Still there. It's just that we are currently trying to revive the economy. Okay. For today, I will teach you guys. We're going to continue what we learned last week. Goes deeper into power analysis. Okay. There are two concepts behind power analysis. The first one is distribution. And we have to know whether our sample is normally distributed or not. And then the second one is we have to know the level of significance that decide our confidence level. Okay. In the statistical analysis, doesn't matter what kind of analysis, especially for a descriptive statistical analysis, there are four quantities that have very close relationship. Okay. We have to know the sample size, the effect of our number of size, the number of sample, and then our type 1 and the type 2 error. Okay, so we want to rule out that our conclusion is not highly chances to be in the type 1 error. By all means, as I would like to remind you guys, type 1 error is an alpha, and the probability that our finding, the effect that we find is not there. So basically accusing the innocent is guilty. Okay, and then we have to rule out another type of error, which is a type 2 error. Okay, by the way, what the type 2 error means is probability of finding an effect that is there. We decided that the guilty person is not guilty while they are actually making a crime. Okay, so this is what we want to rule out. So the power of the statistical mainly coming from the ruling out the possibility of type 2 error. When it comes to statistics, and probability is either between 0 to 1 or 0% to 100%. So the way we write our statistical power, the way we write our equation is just by 1 minus the type 2 beta, the type 2 error, this is our power, statistical power. Okay, so there are two types of distribution: the population distribution and the estimated population distribution. In the statistical analysis or in any study, we always do the estimated population distribution. We are rarely do any form of estimated measuring the actual population distribution, unless you have enough funding, big enough funding to cover the whole population. Looking at you're assessing the population that when the numbers of the population are very, very low, then that is feasible. Unless if you are dealing with some sample that are very large, for example, like measuring the whole human population, that would be inconvenient, that would be very difficult to achieve. So we're taking sampling as much as we could based on the cost that we could afford. Okay, and usually we delve into the estimated population distribution. Okay, so when we talk about distribution, we always talk about the normal distribution. Okay, the normal distribution, also known as the Gaussian distribution, it has many shapes. Okay, we have a very steeper, the blue one, and then we have slightly wider distribution, a distal normal distribution, and then we have a distribution that's skewed a bit to the left or can be to the right. Okay, it comes in many shapes, but then again, as long as you can plot them into a bell shape, those distribution are also known as a normal distribution. Okay, so when it comes to normal distribution, we're looking at the mean. Okay, the centered value of the population distribution, the peak. The point is, if you are measuring the population distribution, the peak is the mean and also equal to the median. And then the wide of the distribution, we have that cover about 95% of the population are known as the standard deviation. If you're looking at the symbols, these are the official symbol, the X bar or the mu indicate the population mean. All right. But for the standard deviation, the symbol of sigma. Okay. So, as I mentioned, we rarely measure the whole population. We usually take a sample out from the population. For example, in this instance, we take 5 samples. We measured 1, 2, 3, 4, 5 samples. So we have the n of 5. And then we calculate the mean. All right. And somehow the mean of the our sample is different from the population mean. At the same time, you guys notice the median of your sample always not going to be equal to your mean. All right. If you measure the whole sample, the whole population, we will get our mean and the median going to be on the same. Going to be equal. In this instance, when we're sampling our sample, when we do the sampling and we measure the mean, the average of our sample, it will be different than the actual population. Of the mean of the actual population or the mean of the actual distribution, we cannot know that. It's very difficult for us to. We usually deal with the one that we sample, okay, and as well as we also dealing with the median as well, the standard deviations. And you guys notice that the standard deviation in the sample also going to be different than the one on the actual standard deviation on the whole population. Okay, so what we have here, we have the standard deviation measured or calculated based on the sample that you collected. Okay, but then again, it's represent the standard deviation, still represent 95% of your data. So again, if you repeat the experiment, we do it and we repeat the experiment, we take another samples. All right. And then we found that our second experiment sometimes is going to be different than the one on the first experiment. Okay. So when we repeat, we're going to find that the mean is different from our samples because it has much more wider distribution. And also the standard deviation is also different. And then we repeat again. Okay. Same cases here, therefore we repeat for the second time, which is our third experiment, the same conditions, same sampling location, same species, or whatever it is. You guys would notice that now we have another mean for this particular experiment, this particular repeat. Okay, and the standard deviation, this time we've compared the 3 standard deviation is going to be different with each other. Same cases with the mean as well. So if we repeat the experiment again and again, most likely we're going to have a different means that pretty much going to cover the whole population. So what does it mean? So when we have different standard deviations, when we have different means, when we calculate the differences, the variance or the standard deviation of the mean, what we get is the standard error. Okay, that's what we call the symbol for standard error is standard error of mean, SEM. Okay. We calculated the standard error from the standard deviation of the mean instead of our actual sample here. We call the standard deviation of the mean. Now we're calling them as a standard error. Okay. There are other type of standard error. We can call them if we're measuring the standard deviation of the standard deviation, we call them the standard error of the standard deviation. Okay, we're not going to involve dealing with the standard error of the standard deviations. What we're going to measure, what we're going to deal most of the time in biology for you guys is measure the standard deviation of the mean. Also, another name is the standard error. Okay. Another way that I teach you guys during the practical session is by measuring the whole population mean and then get the sum, get the standard deviation in Excel and divide it by the square root of the number of population. This is the best way to get your standard error of mean. Okay, if you find now you have all the sample together, since it's coming from the same population, you guys could pull them together and calculate its actual mean. Okay. So, in summary, population distribution are not the same as estimated population distribution. And you guys found that most of the time we estimate the population distribution. And you guys find the mean of the population can be different from the mean of the measured samples. Okay, it's not always the same. Okay, and you guys find that median and mean, or the average of normally distributed population, should be equal. However, the mean and median of your collected sample you measured them is not going to be the same. There is a little bit differences. Okay, if you have a evenly distributed samples, then your mean and median going to be the same. But if you have an outliers in your samples, it will affect your median and your mean calculation. Okay, the standard error of mean is basically is a standard deviation based on your measured mean. Okay, based on the calculated mean between your repeats. When it comes to the statistical analysis, the issue is here, how can we scientifically differentiate data from the different population distribution? Okay, so for example, we do two treatment. We have two conditions. Okay, now we have two possibilities. Okay, if we are looking at, for example, two treatment or two population, if we want to make comparison between two conditions, there are two assumptions that we should make. The first one is either the measured data coming from different distribution, your first distribution, which is, for example, your untreated, and then your second data coming from the second population. Or is it going to be coming from the same very wide distribution? If we're looking at the example here, we have the untreated and this other value, and then we have the treatment, and the condition being treated with A drugs. Okay? When we do the treatment, there are two possibilities. Okay? Could be that your data coming from two distinct populations, all right, coming from two distinct populations, the first distribution or second distribution. Okay? Or it could be coming from one distribution. So we have to consider these two possibilities every time when we do the analysis. Which distribution does it coming from? All right, is it coming from the two different distributions, or is it coming from one same distribution? Can be two possibilities. So how can we define whether our sample coming from which distribution, between the first or the second one? Right. Again, now imagine if we have multiple conditions, more than one treatment A, drug with drug A, B, and so on. Is it coming from either multiple distribution, or it can be coming from one distribution? So the best way is by looking at the level of significance. So you guys remember the level of significance indicates the statistical significance, the p-value. All right, what the p-value meant is the probability of obtaining a result equal to or more extreme than was observed in the data. Okay, by all means, is the p-value less than equal than alpha, which is, remember again, the alpha is your type 1 error. We can reject the null hypothesis. So what does it mean here? It meant that the sample coming from different distribution. Conclude that your sample are statistically significant. If your p-value above than the alpha, what does it mean is we fail to reject the null hypothesis or accept the null hypothesis. What does it mean here? It coming from the same distribution. By all means, in the statistical analysis, for example, if we measure the differences, your data are statistically not significant. All right. So usually the alpha, as I mentioned to you guys before, we set at 0.05 or 5% or lower. Okay. So when the p-value lower than the alpha, for in this instance 0.05, you want to be more stringent at 0.01, you guys can conclude that your data coming from the two distribution, and you could rule out that your samples coming from one same distribution. Okay, so we're talking about the probability. The probability of your data going to be from two different distributions. Okay, thus we consider as your two data is statistically significant. Okay, when we have the p-value above the alpha, so what does it mean here is we cannot rule out the possibility that your data coming from one same distribution. Okay, these are the most likely possibility, whether although you do the treatment, it's still coming from the same distribution. Therefore, we consider as not statistically significant. Okay, in summary, we can increase the likeliness of our data from different distribution by testing the alpha, and usually we set the alpha at least at 5%, or you want to be more stringent, you could set at 1% or 0.01. Okay, when the p-value less than the alpha, what does it mean here? You are basically reject the null hypothesis, indicate that the sample coming from different distribution, therefore your measured condition between, for example, between two drugs is considered as a statistically significant. While if the p-value above than the alpha, what does it mean? You are unable to reject your null hypothesis. By all means, you have to accept your null hypothesis. So your measured sample, although you do the treatment do not have any significant differences, or conclude that it is coming from the same distribution. Thank you.